Hi. Welcome. Thank you all for waiting. My name is Rich Hickey, and I'm here to talk about Clojure. It's a programming language I developed to solve a number of problems, one of which was how to write concurrent programs easily. So tonight's talk is going to be sort of a general overview of Clojure and a specific look at some of the concurrency support that's built into the language. So I'm going to start with a little introduction. As I said, I'll give you a quick tour of the features, but one of the things I really would like to do tonight is look at a piece of software written in Clojure. And so I'd like to, hopefully, if I can move at a good pace, get through my slides and sort of the ideas behind what I'm going to be showing you, and then look at some code, and hopefully we'll have more opportunity to look into the syntax of Clojure and some of its features when we're looking at this program. We'll see some of the things in action. So quick feature tour. Then I'm going to set up sort of the problem space. In particular, talk about shared state, how we do it today, how you do it in C#, Java, or C++. What happens when we get into a multi-threaded context, and specifically what are some of the current solutions for that in those spaces, locking in particular. That's something I've done a lot of over a long period of time, and I'm tired of trying to get right because it's simply far too difficult. So I'll set up some straw men there, and then we'll turn and look at what Clojure does. And tries to solve these problems in a number of different ways. So refs, transactions, and agents are features of Clojure. And then we'll do the walkthrough. We'll look at an actual program. It's kind of a cool little ant colony simulation that's multi-threaded, has some graphic components, and something that would generally be hard to do correctly in most common languages. And then hopefully we'll have some time for questions. Questions throughout are okay. As I said, I'm going to try to go quickly in the early going, but at any point you have a question, don't stay stuck. So I'm a software developer. I've done a bunch of things: scheduling systems, automation systems, audio analysis, fingerprinting, election projection systems, and machine listening software. I'm an architect and specialize in blank paper, new designs, hard problems, things like that. Worked in C++ and Java and C#, Mathematica, Common Lisp, Python, a bunch of other things. And so I'd like to try to get an idea quickly of where you're at so I know what not to bother with or what you need to hear. How many people here use Lisp at any point, Common Lisp or Scheme? Okay, that's good, about half. And then how about the Java, C#, Scala thing? So almost everybody does that. Anybody with any ML or Haskell? Just a couple. Okay. Python, Ruby, Groovy. Okay. How about Clojure? Anyone using or trying Clojure? A couple of people in the room. Okay. That's neat. And then how about multi-threaded programming? Anybody? Okay, so about half. So those will be the people who've grown in acknowledgement as we get to all these points. Great. That's a great audience. It seems like the ML Haskell side is least well represented, and the few people here who have that will be the ones nodding in acknowledgement at some of this, I think. When you come to Clojure, you'll see it has three main flavors to it. One is an interoperability with Java. It lives on the JVM. But I get people coming to Clojure from Scheme who've never used Java, who are like, oh, what's this dot, and where do I put it in between what, and what is Java doc, and where do I find it? And then there are people coming from Java who are like, what is Lisp? What are all the parentheses and everything else? And I don't get as many people coming from ML or Haskell, mostly because I guess by the time you've figured out Haskell, you're tired and you're just going to stay there. You know, a lot of Clojure is inspired in particular by Haskell and ML. ML also is a definite thing. And for tonight's example, ML will be poignant. But Clojure kind of plays in the same space as Python, Ruby, and Groovy in being a dynamic language that's as accessible, I think, as those, but as performant as Java. And I would like to believe is useful in any context in which you would use Java, not just for scripting or lightweight problems. So some fundamentals of Clojure. It is a functional language. You may hear people say, oh, you can do functional programming in Lisps or Scheme, and you can mostly by convention or good habits. But Clojure is functional sort of like the way ML is functional. In other words, you can't change things, pretty much. Most of the data structures are immutable. And that has a lot of value to a program. But it's going to have particular value when we talk about concurrency and what it takes to make a program safe in the presence of multiple threads. So it's functional. It has immutable, persistent data structures. I'll explain what data structure persistence is a little bit later. There are no mutable local variables. You don't do traditional looping by iteration and mutation of a counter or anything like that. So it's much more functional than most Lisps, probably the most functional Lisp. But it is, in fact, a Lisp. Most people here have touched some Lisp, and I would say a characteristic of a Lisp that sort of crosses through all the families is the fact that code is data, that there's a reader, that the language is defined in terms of the interpretation of a data structure and not in terms of a stream of characters and the syntax for, you know, a grammar with characters. And Clojure is a Lisp in that sense. It is in many other ways. It does have parentheses and S expressions and things like that. But it's a Lisp at the core philosophical level. But it is not Common Lisp or Scheme. I'm not going to have enough time in tonight's talk to draw a lot of contrasts. And the one thing I would say is when I get people coming to Clojure that have experience with Common Lisp or Scheme, they have to be reminded sort of almost continuously to not suppose things. You're going to look at things. Reuse some of the same names. Some syntax for different meanings, almost opposite meanings. It's not a superficial thing, and it's not just to be different. There are reasons why I use the names I do. One of the reasons is there are only so many good names. And if they have to mean what Common Lisp said they mean forever and ever and ever, that's not fair. So they mean different things. So you may have a presumption when you look at some code, because it looks similar. I've seen two parens around this and that word. Just to take a step back, maybe what you're supposing might not be correct. If it really seems to be a clash with what you think it means, you know, I'll clarify for you. But just remember, it's not Common Lisp for Scheme. It has no backwards compatibility with those things. It makes no presumption of bringing code from those languages into Clojure. It's a new Lisp. Another fundamental of Clojure, it is hosted on and embraces the JVM. I'm leaving out the rationale part of this talk so I can get to the concurrency things, but I believe it's important for new languages to embrace a platform like .NET or the JVM because there's too much wheel reinventing on the parts of new languages. Every new language invents a whole new library for doing the same old things, talking to a database, talking to XML, sockets, and I think there's no reason to do that. You know, there's languages and there's libraries, and when you go to a framework like Java or the JVM, the libraries are substantial. Like Clojure has the most libraries of any language. That's fair to say because it has its own plus Javas. And Java has the huge libraries. There are other aspects to that, though, that matter. For instance, when Java is your implementation language, you have a major advantage over Lisps that are hosted, for instance, on C, in that your hosting language shares a memory model and a garbage collector with your hosted language, which means that things that used to be foreign function interfaces and kind of ugly, potentially, now are really nice. And you'll see that Clojure embraces the JVM bidirectionally quite extensively and to its benefit. Another fundamental of Clojure, if you're going to say Clojure has 4 legs, it's functional programming, Lisp, being hosted on Java, and the fourth is concurrency, direct support for concurrency, primitives for concurrency, and a design to support concurrency that pervades the entire language, including the data structure design. The last point of Clojure is that it's open source and accessible and downloadable in this version, and you can participate pretty directly. So it's not a proprietary thing. So I'm going to quickly do, mostly enumerate the features of Clojure briefly before we dig in. It supports dynamic development like Lisp. So you've all experienced that in Lisp, a REPL. It has a reader. In particular, Clojure is not interpreted. It is always compiled. Everything you enter that's evaluated by Clojure is compiled on the fly into JVM bytecode and loaded. So everything is bytecode. There is no interpreter in Clojure. It has all the basic primitives, numbers, arbitrary precision, integers you're used to from Lisps, ratios, characters. Strings are Java strings, so therefore they're also immutable strings. Symbols, keywords, it has regex literals and some other things like that. In addition, Clojure has a set of aggregates. It has the classic Lisp-like lists, with the difference being that they're guaranteed immutable and persistent. There's no set car or replac A or anything like that. In addition, it has maps and sets and vectors, and these are as first class in Clojure as lists are in Lisp. Don't say that too fast. Which means that maps are readable. There's reader syntax for them. There's printing for them. Ditto sets, ditto vectors. All of these are persistent, immutable. Again, persistence I'll talk about in a little bit. And they're extensible. All of the data types in Clojure are represented by abstractions. There are interfaces in the Java side, which means that they're not hardwired. You know, in Lisp, traditionally, a whole library is built around const cells. But it's hardwired to those const cells. And you know, many people are frustrated by Common Lisp's inability to extend the sequence library to their own data structures. That's not the case in Clojure. All of the data structures are defined by interfaces, and all of the useful library is defined in terms of abstractions, not in terms of concrete things. The big one is the sequence library. Big sequence library. Everything that used to be built on top of consts is built on top of this logical thing called the sequence. And the sequences are supported on all the data types, on strings, on all the Java collections, anything that's iterable, which means your library, any work you do on logical sequences works on everything, not just lists. Clojure supports metadata as a first-class entity. That means the ability to associate related data with a data structure without impacting its equality semantics. So you can have two vectors that contain 1, 2, 3, and 4. They're equal. But this vector can have a piece of data that says, I got this from this internet site. And this one can have a piece of metadata that says, I found this on the road outside. And they're equal. Their values are equal. But their metadata is different. Metadata is sort of an open system. I don't dictate its use. But you can use it in your own programs to check sources, like I just described, whether or not things have been validated, where they came from, have you ever looked at them, how old are they, things that are not really part of their value proper, but are about the data. That's what metadata means. There's direct metadata support for all of the interesting data structures in Clojure. There's reader support for it. It's a first-class concept. And I think Clojure is kind of unique in having that. It has the typical Lisp things. Functions are first-class data types, closures. It has a functional looping construct. It does not have proper tail call optimization, and that's because the JVM doesn't. And Clojure uses the JVM calling architecture, both for performance and interoperability. So Clojure is very fast, and Clojure calls are Java calls. They use the Java stack, but the B side of that is that I can't do tail call optimization as in Scheme, which means I can't offer recursive calls as a method of doing loops, as you can in Scheme, although you can't in Common Lisp. So what Clojure has is a first-class functional looping construct that is recursive and is functional and feels exactly like you would do with function calls in Scheme. It is less general than full tail call optimization, but it's what I can do on the JVM, and it's quite pretty, I think. So it has that. It has an extensive destructuring binding system, not just for lists. Does everybody know what destructuring binding is? Okay, it's where in a context where you would bind variables, with names, that you can not just put in variables, but you can put in things that look like data structures that mirror the data structure you're getting passed, and can pick out and name pieces of the data structure you're being passed. And that's called destructuring. In Common Lisp, it's available in the macro system and as a standalone function called destructuring bind. But in Clojure, it's built into let, fun, which is lambda of Clojure, and loop, which means that all of those constructs can destructure their arguments. And they can destructure very interesting things, including sequences generally and maps. So it's a very powerful way to write elegant things. If you have pattern matching MV, this is half of that, except the part that I don't like, which is the conditional part. It has list comprehensions in a construct called for. It has macros, and they're common Lisp style macros, although Clojure is a Lisp 1. And typically there was an argument that you really couldn't have a Lisp 1 with hygienic macros, without having hygienic macros, without being a disaster, and that's why Common Lisp is a Lisp 2, which means it has a separate namespace for functions. But it ends up that this is a solvable problem. It's solvable with a combination of two things. One is that you have namespaces, which Clojure does. So you can segment your names into namespaces. The other thing that you need to solve this problem by having sort of Common Lisp style macros, procedural macros, in a Lisp 1, is to distinguish between symbols and variables. And in Common Lisp, they're sort of unified, so when the reader reads, it creates data cells, because symbols are places. In Clojure, that's not the case. The reader reads symbols, and symbols are just symbols. There's no storage associated with them. And there's something called vars in Clojure, which compilation will find, given a symbol, the var to which it corresponds. That's a storage location. So it has macros. They're Common Lisp style macros. And therefore, they're a lot of fun and very powerful and arbitrarily powerful, because you write little programs that can transform one piece of code into another. So Clojure has that. It has multi-methods, which is a way of doing polymorphism without any inheritance. Clojure multi-methods are completely general. Essentially, you have a function and it takes arguments. You can say, I'd like to dispatch this differently depending on what the arguments are. And it doesn't have to depend on the types. It can depend on the values of the arguments, sort of an arbitrary way to do dispatch. So if you're familiar with virtual functions, they always dispatch on type, right? If you're familiar with Common Lisp generic functions, they always dispatch on type or value of the arguments. Multi-methods take that one step further, and they say dispatching is a function of the arguments. You can say what that function is going to be. It can pick out the types, it can look at the values, it can go ask a database. Then the dispatch function returns a value, and dispatching happens on that. It's probably impossible to understand from that brief a description, but it's a way to support polymorphism that's independent of inheritance. So it's pretty powerful and very flexible. In particular, because it's independent of inheritance, it allows you to divide up your data space into multiple hierarchies, which is typically hard, to have multiple taxonomies in a single program. That's easy in Clojure. And Clojure has concurrency support, which we're going to hear a lot about. More and more, Java. Of course, it's hosted on the JVM. Hopefully, it has decent Java interoperability, and it does. You can certainly call methods of any Java classes, instantiate classes, access fields, access arrays, create arrays, fill them up, anything you want to talk to Java. In addition, you can create proxies for interfaces and classes, which essentially allows you to implement those classes. And we'll see a little bit of that in the demo program. The whole sequence library, because it's written in terms of these abstractions, is extended to Java types. So you can write algorithms in Clojure that manipulate Clojure's logical sequence. Those algorithms will work on Java strings, Java arrays, anything that's Java collection, anything that's Java iterable, which is pretty much anything interesting in Java. In addition, going the other way, where it's appropriate, Clojure data structures implement Java interfaces. All the Clojure collections implement the read-only portion of collection. Obviously, they're not writable, so they opt out of the optional part, which happens to be the writable part of collection interface. Clojure functions are callable, so you can just pass them right to the executors framework to execute them in threads in Java. All Clojure data structures are iterable. Things that can be are comparable, et cetera, et cetera. So there's a great ability to create some data structure in Clojure and hand it off to Java and have Java be able to consume it without any conversion or transformation because of these interfaces being implemented. And much, much more. It has namespaces, as I mentioned. It has functional tree zippers, XML support, and inspectors, and all kinds of neat things, which you'll have to look at the website and find out more about. We'll see lots of this used in the program, but not all of it. Any questions? Is this too fast? Okay. Okay. Now we'll get to the meat of it. State, you're doing it wrong. Which is okay, because I was doing it wrong too. We were all doing it wrong. I think one of the things that drove me to Clojure, and you have to be driven to do something like write a new language, because it's definitely an act of insanity to do. But one of the things that drove me to it is that I'm completely convinced that mutable objects and the whole approach that's sort of implied by the design of Java, C#, Python, all the languages that have followed along this path is very much the wrong way to do most things. It's an okay way to do some things, but it's the wrong way to do most things. Mutable objects are the new spaghetti code. And by that I mean that you eventually, with mutable objects, create an intractable mess. And encapsulation does not get rid of that. Right? Encapsulation just means, well, I'm in charge of this mess. But the real mess comes from this network that you create of objects that can change. And your inability to look at the state of a system and understand how it got there, how to get it there to test it next time. So it's hard to understand a program where things can change out from underneath you. It's very hard to test it. I think it's very interesting and telling. All the emphasis on test-driven design. And I think people are driven to this because they know these systems are completely intractable without constant testing. But rather than question whether or not they were doing using a decent language in the first place, or maybe this wasn't a good idea, they're just going to test it to death to try to keep it running. And I think it's better to question the fundamental principle about whether or not you really should have this much mutability in your program, because the vast majority of most programs don't need it and shouldn't have it, and would be easier to understand if they didn't have it. Anybody that knows Haskell is going, yes, yes, of course, yes. And Haskell is great. I think it's not the only way to achieve that. I think Clojure is in a unique position in providing maybe the friendliest face ever presented to functional programming. I think that's out there, because you end up doing this programming with these immutable data structures, and it's not too painful. And then you realize, wow, I'm worrying a lot less than I usually do when I write programs, and I have less stress, and I can just bravely go and hand this data to some part of the program I don't understand, because I know nothing bad can happen. And that's a good feeling that you want to achieve. So that's the first, hard to understand, test, and reason about. But if you put concurrency in the mix, there's no doubt about it. Mutable objects are a disaster. They're a complete catastrophe, and I'm going to show you exactly why. But I want you to understand that you don't have to believe me. I even carried a book this whole way. Well, I just drove, so I didn't actually carry it. But has anybody read this book, Java Concurrency in Practice? How many people have read this book? Oh, boy. And all these people are programming in Java? You have to read this book, because it's a fantastic book. And it's a book that will scare you to death, because what it basically says is this is impossibly hard. It's just so difficult to get right. But the other thing you're going to see if you were to read this book is the mention of immutability over and over and over and over and over again. Just if things were immutable, there would be no problem. The problem is it's hard to do things immutably in Java because you're fighting, you're fighting the stream. You're running upstream, trying to do the right thing. But it ends up being the case that if you can use immutable data structures pervasively in your programs, concurrency becomes very much easier. It's not everything, and you'll see in the infrastructure that's in Clojure, you need something beyond immutability. You need some coordination mechanisms to fully solve the problem. But there's no doubt about it that mutable objects are really bad for concurrent programs. So as a default architecture, I think mutable objects are terrible. They really are, and we need to start questioning whether or not that's the right way to start. I don't care how much you test. Do the right thing, and you won't need this kind of testing. And you'll still have a more reliable system. But one of the things I came to was, I decided I knew what the right thing was, and I started coding all my Java and C# in a completely bizarre manner with no data inside the objects. Everything was a static method that took data and returned data. And so I did functional programming in C# and Java. And it's very hard because it's not idiomatic. And people would look at my code and be like, oh my God, what happened? Why is this class with 27 static methods and no data? I love that. And I try to teach young programmers to do that. If they're stuck in Java and C#, their programs will be better if they're functional. But functional programming in languages that default to object-oriented programming, especially mutable objects, is very difficult. So, you can do all the testing you want, but I think languages matter. I think that a language that does the right thing sort of by default makes everything easier. And unfortunately, there wasn't one in the space I wanted, which was to target Java and have it be a Lisp. Therefore, the act of insanity that is Clojure. So let's talk a little bit about the problem of concurrency. What do we mean by concurrency? We mean things happening at the same time. I mean, that's what it really means. Whether or not things are happening at the same time depends a little bit on whether or not you have more than one CPU and what your operating system is and what platform you're running on. But certainly Java and the JVM is capable of simultaneous execution. That is, multiple threads are running on separate CPUs at the same time. But even if you don't have actual concurrency, if you use threads at all, you have simulated concurrency, which means you have interleaved execution. A little bit of this process happens, a little bit of that, and back and forth. So even on a single CPU, as soon as you have a multi-threaded program, you have the problems of concurrency, which is that you would like to avoid seeing inconsistent data or producing inconsistent data. And that ends up being a difficult thing to do. The more components there are in particular, the more difficult it is. The more steps involved in an operation that you want to perform in your program. In order to do this, I need to take some money out of this account and put it over there, but check with the account manager, and these 7 things happen, and that's a unit of work. If you want to make that unit of work happen or not happen in a program, of course in the database there's transaction support that makes this easier, but in your program you have similar kinds of things you need to achieve. That's all on you. And the more steps there are, the more difficult this becomes. There are also aspects of concurrency related to parallelism. There are parallel programming languages and languages that support automatic detection of the ability to employ parallelism. You just say, do this to everything in this sequence, and the language figures out, well, because everything's immutable, I could put this on, split this into 2 jobs and put 1 job on each CPU. Clojure doesn't do anything like that. It's not really a parallel programming language. And so the emphasis here is going to be on the coordination aspects of programs that are concurrent, where the concurrency comes from your deciding to execute things simultaneously, not the systems deciding to do that. Everybody get what concurrency is about, what we're talking about today? Okay. So this is the straw man part of the thing. I'm not talking about Clojure here. I'm talking about what you have to do today if you're programming in, let's just say, Java and C#, because we had almost unanimous recognition of those 2 languages. So what do you do now? What we're going to talk about is what do you do now if you wanted to manipulate a collection in your program from multiple threads? Well, you could lock it, right? You could lock it or it's synchronized, right? And inside that block, you'd have exclusive access to the collection. So we use locks. Only one thread can have the lock at a time, right? Everybody else blocks, waiting for that. It requires coordination. In particular, you have to choose to do this, right? Any code that's going to manipulate this collection has to know, oh, I think other people might be using this, so I better lock it when I look at it or change it. And so it's manual, and you have to decide to do it. It's a convention. Of course, you could say, well, you could have synchronized primitive in Java, on the Java side at least, which they've fallen out of use of because it's really not that useful. It only can handle one method interactions. So if you need to like check if something was in a collection, and if it wasn't, put something in, that's 2 steps. So synchronize doesn't help you with a 2-step job. So you have to lock it, and then you can do those 2-step jobs. So there's locking. Everybody has used locks, yes, at some point, hopefully. So what's wrong with this? What are the problems in doing this? Well, you can't enforce it, right? Everybody has to choose to do this. If you forget to lock in your part of the program, you've just made a mistake. And the language is not going to help you detect this mistake. There's nothing in Java or C# that helps you with this. So there's no enforcement. That's a big problem, because keeping track of what things you have to lock, you don't lock everything you touch, right? In your programs, in your Java and C# programs. No. You have to decide, well, I think this is something we're sharing, so I should lock this thing. That's a big problem, because what happens is you decide later that you're sharing this thing. Well, all kinds of access to this thing is throughout your program now. Those people didn't make that decision. You have to go and figure out where to retrofit the locks. Even when you put the locks in everywhere you should, you have a bottleneck that comes from this on multi-CPU machines, because these locks are sort of super powerful, global, no one's getting in here, and everybody else that wanted to touch this thing is waiting. So it can cause a bottleneck on a multi-CPU machine, and guess what? You're running on a multi-CPU machine. This is no longer a maybe someday. This is definitely happening on the most mundane hardware. We've got multiple CPUs, and it's only going to get worse because they can't make the CPUs faster, so they're making more of them. Yay, lucky us. Another problem with the single lock is that it really is too much. For instance, readers block other readers, which is kind of a shame because they're not really going to interfere with each other. But because you're locking as a reader to prevent a writer from messing you up, you're also locking out other readers. So that's inefficient. So how can we fix that? Because there are solutions to the read parallelism problem. And the solution is a special kind of lock, not the one you get for free by using lock or synchronized in C# and Java, but one you manually ask for, which would be something like a multi-reader, single-writer lock. And these have special properties. In particular, readers don't block each other. So multiple readers can be in there reading, and they don't block each other. So that's an enhancement to the parallelism support. You only get one writer at a time with one of these things. Writers still wait for readers in this strategy. But it's better for read parallelism. So that's one solution. What else do we have? Copy on write collections, not in C#, but in Java we do. Anybody use copy on write collections ever yet? They're kind of an unusual thing, but they have very neat multi-threaded properties. In particular, what happens in a copy on write collection is when the collection is changed, inside the implementation of the collection, a copy is made of the data, and then it's atomically swapped in for what the data that was there. Which means that whenever anybody reads, they get a copy of the data that was there. That is never going to change, because what's going to happen is a new set of data is going to get swapped in. So reads are lock-free. Anybody that wants to read a copy on write collection can read it freely, and there's no locking associated with that. Writes are atomic, because you sort of prepare all the data over here, and then with an atomic compare and swap operation, swap in the data. It appears to change instantaneously. So those are actually lock-free as well, because compare and swap is a lock-free operation. It leverages a processor primitive that can change a memory value atomically without anybody seeing an in-between state. The problem with copyright and write collections, I mean, those are really nice properties. Now we're completely lock-free. No blocking in readers, no blocking of writers by readers. Lot of nice things. The problem in general with copy on write is that it's very expensive to write because it's usually a full copy. So if you read the docs for copy on write array list, I think it's called in Java, they'll say, you know, this is for mostly read situations, occasional write situations. If you're writing a lot, this falls down. And there are still limitations. A multi-step interaction with the copy on write collection still requires a lock, right? Which makes sense because, you know, if I'm going to change this and that, and maybe I need to read it in between, well, somebody else could get in the middle of that. And nothing about it atomically swapping is going to help that. So if you have a multi-step operation, you still have to lock. So this is not a cure-all. But that's basically all you get, right? There's nothing better in Java or C# today than these solutions. And then we're still only talking about a collection here. There is, in fact, another way to do a data structure that has much better properties for concurrency. And it's called a persistent data structure. And unfortunately, persistent is one of those words that it's used over and over again in programming. Most people, when they hear persistent, they think of putting it in a database, storing it somehow, being able to serialize it. That's not what this notion of persistence is. When we talk about a persistent data structure in functional programming, what we mean is that the data structure is immutable. And so what's going to happen is when you want to produce a changed version of the data structure, you're going to have to produce another data structure. Okay? And what we want to have happen is when we produce the new data structure, we want the old one to remain accessible. There are recipes for producing new data structures from old where the old ones shouldn't be used anymore. And that's not true persistence. In true persistence, the old version is still there. So I can have something, you can get a changed version, my thing is still fine, your thing is fine. Both can't be changed. But the trick with the persistent data structure is, for whatever kind of data structure it is. So for a list, you have constant time access to the head, linear time access to the middle. For a vector, you have constant or near constant time access to anywhere, random access, right? And if it's an array list, maybe constant time insertion at the end. For a hash table, you expect constant time, random lookups by key. Whatever your performance guarantees are, you know, in the big O notion for your data structure must be maintained for a persistent collection to really be considered a persistent collection. Otherwise, it'd be like copy on write. I mean, I can take your hash table and make a new hash table and just shovel everything into it one by one. But what's the cost of that operation? It's linear in the size of the collection. Well, that's not the behavior of hash tables. You expect, you know, an insertion to be constant time, not linear. So a persistent data structure maintains the performance guarantees of its operations across changes. So it's a big difference with copy on write. I'll show you how it does that in one slide. But the implication of that is that the new versions can't be full copies, right? If I'm going to I have a hash table here, and I'm going to have a new hash table with one new entry in it, and I'm not going to have that be linear time to copy everything, then somehow it can't be a full copy, because a full copy would have to touch everything. So they have to share structure, and I'll show you one of the ways that happens. But already, this is sort of a magical thing now. I have an immutable collection, and I have a really inexpensive way to make a new version of that with a small change to it. And they share structure, which means they have good memory characteristics, and all the performance guarantees are still met. This is like magic. It's really, really good. And it is really, really good stuff. If you've been programming in Lisp, you've been programming with a persistent collection, as long as you haven't called setcar or replace all along, which is the console. Right? If you use a console in a functional manner, it's a persistent data structure. If you cons onto a list, do you affect the original list? No. You get this new list that shares a tail with the other list. Its tail is the other list. That's an example of a persistent data structure. It's a very, very simple persistent data structure. But it does show you sort of what's involved. There's shared structure, and there's sort of a recursiveness to the definition of the data structure. You know, this new list is the old list with one more thing at the front, sort of a recursive definition of a list. And certainly Scheme's whole heritage of recursion and lists is about that. It ends up that, in my experience, there's no way I could have written the programs I've written over the course of my career without vectors and hash tables. There's simply no way. I don't think production code can survive without data structures with those kinds of performance characteristics. So lists are not good enough. Even trees with traditional log n kind of performance are not good enough for the programs that I've written. Certainly a lot of people writing in functional programming languages are okay with log n trees. Typically, the way to implement a persistent data structure is to use some sort of a tree. Right? For a list, it's linear, but when you start talking about a map, you say tree. And vectors, you don't even do. It's still a research topic, how to do a purely functional vector. But I knew in Clojure that I needed persistent data structures and I needed vectors and hash tables. And I spent a lot of time researching and designing a persistent hash map and a persistent vector, which sort of they're the magic secret sauce of Clojure. It makes Clojure a high-performance language with all the functional goodness. In addition, Clojure does have a sorted map, and that's, you know, sort of a classic functional red-black tree implementation. So how do you do a hash map tree thing with any kind of decent performance? It is still a tree. It ends up that the way you do a really fast hash table is to use a tree, and to use a tree with a very high branching factor. In fact, the factor is 32. And you still use hashing. So what you end up with is something that was originally started by this guy Bagwell. He wrote the paper, and if you search for array mapped hash trees or tries, however you want to pronounce it, and Bagwell, you'll find the paper, the two papers that I read. But his were not functional. So what I did was produce persistent functional versions of these data structures. But the basic idea behind a bit partitioned hash tree is that you take the hash of the value and you mask out ranges, in this case 5-bit ranges, so it's 32 sections, a 32-way branching. And you use as much of the hash in 5-bit chunks as you need to distinguish one object from another in the table. So if you put one in, the first guy in, well, he only uses a 5-bit hash because he's the only guy there. If the next guy is different in those first 5 bits, he's also in the first level. If eventually you have a collision and you get a new guy who's the same in the first 5 bits, the first 5 bits being these light green ones over here, only then will you use the next 5 bits and go one more level in the tree. So you have a very high branching factor, and you're only using as much of the hash and as much depth as you need to represent the objects. This ends up yielding a hash table with very, very good performance. Is it constant time? No. I mean, in technical algorithmic complexity terms, it's log 32n instead of log n. But log 32, that's a really small number. For instance, this is the map for all 32 bits. I mean, you'd have to have a huge data structure to use all 32 bits. And how many levels are we talking? 7 at the most. And it ends up that the first level is partitioned off to the side, so it's 6. So in a gigantic data structure, way bigger than you're going to have, it would be a max of 6 steps. And in most common cases, it's 3 steps or fewer. At the point something is 3 steps or fewer, I don't care if it's log n or log what, I mean, it doesn't matter. That's constant time to me. It's a small enough number that I can ignore it. And there are implementations that are technically constant time that have amazingly high constant factors that are much slower than this. And I've investigated some of the technically constant time vector solutions, which have these amazingly complicated implementations. So this is a really good implementation. The insert times are decent, but the lookup times are stunningly good. Definitely as good or better than the hash table that comes with Java, which is really amazing because this has all that goodness I just talked about. It's immutable and it's persistent. So let's talk a little bit about how do you do the persistent side. The trick is to share structure. Okay, so what would happen if we took this hash table and added something to it. In other words, we made a new version of it with one additional thing, because we don't really change anything. Well, the version we started with is just sitting there. It never gets touched. The new version needs to put one new entry. And in order to do that, it needs to copy the path to the new entry, and only the path to the new entry. Everything else, all these dashed lines, are pointers to things that are in the old data structure, and therefore are shared structure. So the old tree is, this bit over here, and the new one is mostly that, but this right edge is new. Just the path to the new node. So in this case, this was as deep as 4, and you had 4 new nodes to produce a new entry.
You're going to produce the nodes that are outlined in red. You're going to make copies of those.
You're going to make copies of those, correct. And that's what all the dashes are. Those are copies of those nodes. But again, it's very shallow. There are some tricks that are used to make manipulating the edge of this cheap. But this data structure is used both for the hash tables, which use the bits of the hash as the tray, and the vector also works similarly, except there it's the index of the vector that partitions the table, and it fills completely. So these two data structures really let Clojure do what it does, and you'll see the value of that later. So generally, this technique is called structural sharing. It means you produce a new value, and you share as much structure with the original one as you could. In cons, onto the head of a list, that sharing was complete. The entire original list is the tail of the new list. But that's a pretty simple operation, and that's a pretty simple data structure. These are rich data structures with arbitrary insertion. The vector has array list kind of capabilities to insert and grow at the end, so it's not a statically sized vector. And the hash map is a map, a full map. Lookups, make new associations, and all of that. So structural sharing is the key to this efficient persistence. It allows you to keep the performance characteristics there. In the implementations, you'll see everything is final. You'll never see more bizarre classes than you will in the implementation of Clojure in Java. A bunch of classes where everything is final, and you sit there and you say, what utility could this possibly have? And yet, there it is. It's a vector. It's a map. It's a queue. They're all in there. Sets, and they're all final. So it is possible to do this. It's not very idiomatic Java code, but it certainly is cool. And also falling out of this is thread safety, because this data structure can never change. Nothing bad can ever happen by having 2 threads look at it. It's also safe for iteration, and all those nightmares of collections that could change. It throws, concurrent modification exception, right? Everybody's seen that. Everybody's had that happen to them. That never happens with Clojure data structures. So we looked at, there's a couple of different locking strategies. Then this copy on write collections, that's available all on the Java side. Then there's this new notion, persistent data structures. Unfortunately, Java doesn't come with it. But it's possible in Java. The Clojure ones are written in Java. Yet, you don't normally see it. Let's go back a little bit to the locking problem now. Everything I talked about before, that was the easiest thing you could possibly do, multi-threaded. We were talking about only one data structure, trying to control access to one thing. Right? The trickiest thing we had was a multi-step operation on that one thing, which we could lock the one thing and do our multiple steps. That is baby steps in concurrent programming, because what happens is, in real life, you have multiple activities and multiple data structures. When this thread connects, I need to put them in this thing only if they're not in this other one, right? I want to move somebody from this pool to that pool, but I want to make sure they're never in 2 pools and never in no pools. All those kinds of things are very hard, because now all of a sudden you've upped your game. You need to control more than one data asset in the same logical operation. And if we go back to locking, so again, we're not talking about Clojure now, we're talking about what you have to do today if you're using Java or C#. You have 2 options, really. One is what I would call coarse granularity locks. The other is fine granularity. So we'll look at them. In coarse granularity locking, you're going to create some lock over here, and you're going to say this lock is the lock you use to control this set of things. Okay? Whenever you want to manipulate anything in this set of things, you grab this lock. And it's nice. You grab this lock and you can manipulate any of the data structures. What's nice about it is that each multi-part operation only requires the acquisition of one lock. And it's fairly easy to describe this and document this in your, in your program to say, okay, here's the deal. There's A, B, and C over here, and there's a lock for those. And if you ever want to touch A, B, or C, you grab lock, ABC lock. It's very safe. It is the safest if you're going to use locks. It can be confusing if you have a lot of different sets of things in your program. Like one part of your program needs to lock, use A, B, and C, and another part needs to use B, C, and D. Well, is there an ABC lock? Is there a BCD lock? If there is, you already have a bug in your program, right? Or is there an ABCD lock? People have to know what lock do they need to use for what data structures. This is not good from a throughput standpoint. Remember, we talked with one data structure already. It was not good to be locking wholesale for reads and things like that. Now you're talking about multiple data structures, which means there are going to be more people interested in these data structures. Everybody grabbing a single lock or queuing up for that single lock. Lots of needless blocking in this scenario. And you have this question mark of, well, if I'm just reading, should I grab this lock? I don't know. Do you want to do a flying read on some data that might be changing? I mean, sometimes you do. Or sometimes you have to because you can't incur the cost of holding the world down while you read something. I want you to remember that because later we're going to hold the world down when we read something, but we won't really. What's the other option? We go find, right? We knew every object in these programming languages, every object has a lock associated with it. So one of the things we can do is we can lock the data structures themselves, like all the ones that participate in our operation. So now you say, if I need to use A, B, and C, I need to lock A, B, and C, and then I can use them. Move something from A to B and from C, look it up in C, and then move it from C to A, and do whatever I need to do. And any logical operation may require multiple locks. So that's fine granularity. This is a very dangerous thing. This is where most programs end up. Because most programs start with somebody not thinking about locking. And then somebody says, well, we're going to put a socket on the program so we can add this new stuff or have other users come in. And we want to monitor, and logging. And then I need a background thread to generate reports. And you're like, oh my God, now all this stuff that was written nobody thought would ever be seen from more than one thread is going to be seen from more than one thread. And you have this ad hoc locking that goes on. But even with the best laid plans, it's still extremely difficult to do right because you lay your plans and you do that, and then what happens in all programs? Things change. New requirements are added. And remembering what your strategy was when you go back and have to add these new requirements and making sure you account for everything is extremely hard. And in fact, I would almost go to say it's almost impossible. And I sit and help people who are working on multi-threaded programs, and you just have to stare at it and work it through your mind, the possible interactions, all day long. It's extremely difficult. But we know what the basic problem is with this, even before we get into these strategies, which is in formulating a strategy, you need to consider lock order, right? If X wants to lock A and B, and Y wants to lock B and A, you have a problem, right? Because that's a recipe for a deadlock, right? X will get A, Y will get B, X is waiting for Y is waiting for X, you're toast. Your program is over. It's very possible to do this. It's very difficult to enforce locking orders. You have to have conventions. Let's lock things alphabetically. Let's lock them, we'll number them in order to lock them correctly. I mean, that's not a bad strategy, in fact, because at least it's deterministic and mechanical. But it's hard to do. On the other hand, if you can do this correctly, it will give you better throughput than the global kind of locks because there's a minimum amount of blocking. It's just as much blocking as is required for the very few things you're touching. You have the same question, though. Should I lock if I'm reading? You could get very random results if you don't. So let's compare these two concurrency methods. The first is what I would call the conventional way. It's the way you have to do it today if you're not using something very special. And I don't know of anything special for Java or C#. I mean a special language or something that does this for you. And I really want to talk about two things. One is, what's the structure of your program? I mentioned mutable objects or whatever, but there's a structural aspect to a program written with mutable objects, and that is that program is composed of direct references to things that can change. That's your typical C# or Java program. It's full of references, direct references to things that can change. As soon as you've done that architecturally, you are stuck with this locking stuff. There's nothing else you could do. And what do? You lock and you hope for the best. The aspects of this that are bad are it's manual, as we saw. We have to choose to lock. And everything is convention. Every application has to decide, we're locking A before B. We're locking in alphabetical order. There's a lock over here for these three things. Don't forget to lock that when you do this. Right? Where does all that stuff go? It's not in the programming language. It's on napkins or in some doc somewhere or whatever, or in some guy's head. But it is not in your program, unfortunately, and that's bad. We'll contrast that with the Clojure way. And then what Clojure does is two things. We have this immutable persistent data structures, which we talked about. And then we have the acknowledgement that there will be programs in which you need to feel like those things are changing. So rather than have them actually change, because we don't want data structures to change, what we're going to do is we're going to have a reference to something. And we're going to keep that reference around. That'll be a stable reference. But what it refers to, that can change. So therefore, that reference is indirect, right? It's sort of a pointer. It's a cell that holds a pointer to a thing. The cell will always be able to keep track of. The pointer to the thing, that may change. So this cell can mutate. It's an atomic thing that can mutate. And what they're called in Clojure is references. So the different architecture in Clojure is you have indirect references to things that could never change. But those references can be made to refer to other things over the course of an application. That gives you the same effect, right? When we had direct references to things that can change, I could remember Fred, and I could look at Fred at one point in the program, and it would be something. I could look at Fred at another part of the program, and it would be something else. This can achieve the same effect. I have a reference. I'm going to call it reference Fred. At one point in the program, it refers to this. At another point in the program, it refers to that. Same feel. I'll look at Fred. I'll get different information. The difference is this is indirect, right? I don't really have a pointer to this data structure or that data structure. I have a reference that I hold on to. And that those references can change. So now here's a part of Clojure that's mutable. This is the first thing so far I've talked about in Clojure that's mutable. Nothing else you saw. None of the strings, characters, all those data structures, lists, vectors, maps, sets, none of that can change. The only thing that can change are these reference types. And what's important about them is they have concurrency semantics. Because they're indirect, your program isn't just like twiddling them. Your program has to use functions to make them point to different things. And those functions have concurrency semantics, which I'll talk about in a minute, which means that they're automatic, right? The programming language is going to help you change these things to point to other things and not mess that up. And it's enforced. For instance, some of these references can only be changed inside a transaction. And guess what? If you try to change it outside of a transaction, it throws an exception. You can't do that. So there's a big difference now between these two things. One, it's all convention. It's all manual. Things could change out from under you. In the other, things never change. Right? If you actually dereference one of these references, you would get an immutable object. If somebody makes that reference point to something else, do you care while you're looking at this and calculating? No. This will never change while you're looking at it. That's really beautiful. And in the application program, there are no locks. So there's no locking required to do any of the things concurrency-wise that Clojure supports. So I said these things are generically called references. That's kind of a little reuse of the word because you'll see one of the reference types is called ref. So don't get confused by that. So the references are the only things in Clojure that are closures. I mean, you can use Java in Clojure and all kinds of stuff can happen that can change because it's still Java. I don't protect you from the mutation that's associated with Java or side effects. You go there, you do that. But in Clojure, only these references can change. So the only thing that can really mutate. This is inspired by ML. In ML, there's a thing called a reference, and it's a really neat idea. It's the thing in ML that can change. It's standard ML I'm talking about here. It also has arrays, which I won't talk about. But the reference was a kind of a neat idea. The problem for me in just copying that into Clojure was it has no concurrency semantics. In ML, it's just a free-for-all cell. But it was a neat thing because it was indirect, and you didn't need to make mutable composite data structures. If you have an easy way to turn one data structure into a changed version of itself, you don't really need data structures where you can twiddle the bits, right? Because you can make those incremental changes cheaply. So all you ever need is a reference that you can change, and you just refer to changed versions. So there are 3 types of these references in Clojure. There are things called vars, and a var is used actually to hold global variables and functions. So there's a global notion to a var. In addition, vars have the ability to be bound to values inside a thread. And once they're bound inside a thread, that binding is independent of other threads. So I can bind a var called x to a value in this thread. I can bind it to a different value in that thread. And these threads can manipulate x completely independently without interfering with each other. And when they're done with that binding, it unrolls like a stack. I'll explain that a little bit more. But the premise of vars is that vars are for isolating changes within threads. This thread is the only one that will see what it does to x. This thread is the only one that will see what it does with x. So that's one thing you need to do in programs. Another thing you need to do in programs is the most complex case. It's the, I need to move this from this account to that account, and I want to make sure it's in one account or the other, never in both, and never in none. That's a really hard, I need to change 2 things. I need to make that whole change atomic. And for that, you need a transactional system. And the refs in Clojure are for that. So what are you doing there? You're sharing values. You're sharing them synchronously. And you're sharing coordinated changes. Refs allow you to change more than one thing in a coordinated operation. And those changes can be seen from multiple threads. So distinct from vars, which are sort of hiding their changes in threads. Refs make changes that can be seen from multiple threads. And it does that by using transactions. Again, I'm going to break each of these down. So second recipe. So now I want to change multiple things and do that atomically. The third thing you might want to do is you might want to have things change asynchronously and independently, but still be accessible from multiple threads. And agents are the third kind of reference in Clojure, support that. So with an agent, you have something that can change. You can make requests for it to change, and it will eventually do that. But it will do that on its own time, independently. But other threads can see what's happening in different agents. It's a whole different flavor of things. And you use these for different purposes. You'll see in the program I've written, I'm going to use agents and refs. Agents are sort of the workers, kind of make things happen. And the refs are the worldview. It has to change atomically in a composite manner. So let's break these down. I'm not going to talk at all about vars. Other than to say, if you know Common Lisp, they're sort of like special variables in Common Lisp, except they have thread semantics. Common Lisp doesn't have any thread semantics. Some particular Common Lisps do, but Clojure does. So it says what happens when you bind this in a thread. It's independent from other threads. Vars have a stack discipline, so if you bind it to something and then bind it again and bind it again, as the stack unwinds, those bindings unwind, and it eventually gets restored to its root state. That has a lot of utility. You can use it for logging and for context kinds of programming. You can set vars, like very explicitly, sort of like assignments, set this x to be 5. But only if it's thread locally bound, which means that that's going to be a thread local assignment that will only be seen in that thread. They're very cool. I could talk for 2 hours about them. Refs and transactions are the ones I want to talk the most about. So how does this work? Right, I said magically you can change more than one ref, and the change to the set of refs will happen atomically. That smells a lot like a database transaction. In fact, it is a transaction system meant for use inside your programs. A transaction system meant for use inside your program is often called a software transactional memory system. And I've used the term for this. There are people who make software transactional memories that are much more atomic. Clojure is a very application level notion of STM. If you read STM papers, sometimes it's like all these cells, and they're building trees out of these cells. Clojure STMs are about references to aggregates and the system for allowing changes to those aggregates. So what happens? A ref can only be changed inside a transaction, and that's enforced. When you make a change in a transaction, that change is atomic and isolated. Okay, so you know the acid of database, well, it can't be consistent because there's no constraints. It can't be durable because it's in memory. But it has the other two pieces. Okay, it's atomic and isolated, which means that every change you make to a set of refs inside a transaction either happens or none of the changes you made happen. Okay, so that's the atomic. Everybody understands that, I think, that's used as a database. The other thing is that they're isolated. So while you're mucking about in your transaction, you don't see the effects of other transactions, and they don't see yours until one or the other commits. A big difference with transactions in the software transactional memory system, at least most of them are implemented this way, is that transactions are speculative and they're automatically retried. So if I want to move something from A to B, and you want to move something from A to B, and then we both get in and you win, like you get there first, I don't get a failure. My transaction will automatically retry. I'll be second. So that's a unique part, that the transactions will be retried. You sort of get that effect with the database, but mostly by locking. In other words, they just block you until. Now sometimes you get in there, you start doing your work, only to find out, oh, I can't get at this piece I needed to change, or somebody else changed it. But so they'll be automatically retried. A key thing about that is, therefore, your transaction cannot have any side effects in it. Right? If you make a Java call that says print, well, guess what? You may be automatically retried. You may be automatically retried dozens of times. You're getting a lot of print statements. So no side effects are allowed in transactions. You have to only manipulate refs in transactions.
Is there an option that if you have something happening, you say, if I'm not first there, then don't retry? Is there a way to disable that automation?
What tends to happen is that you're going to be looking at data in your transaction, and when you retry, that situation that said your go is not true anymore. And therefore, you will abort because your conditional says, I can't do my job now. If you can, then you will. So that's how it works. There are some transaction systems in Haskell that have like an if-else notion, but I really feel that that's merging a transaction system with a coordination system, and I don't think it's a good idea. So a little bit of details about the STM enclosure. It's very neat in its implementation. Certainly from a user standpoint, it's the easiest thing you could think of. You wrap your code with this sync thing, do sync, and anything that you do inside that is in a transaction. That includes any calls you make, any calls those calls make, et cetera, et cetera. That's a dynamic scope of the transaction. If another transaction is started underneath it, it's absorbed by the parent transaction. So they'll all happen or nothing will happen. And that's it. You say do sync, and you manipulate references inside that. And magically, that work is atomic. And it's magic. Under the hood, it's really, really complicated. And Clojure's STM is kind of unique in that it uses multi-version concurrency control. Does anybody know what that is? Anybody use Oracle or PostgreSQL? Those are database systems that use multi-version concurrency control. The idea behind multi-version concurrency control is that you want to keep readers from blocking writers. And the way you do that is you keep old versions of the data around to support lingering reads. And writers can continue to produce new data. And readers will see sort of a snapshot of the world at the time they were started. That's how Clojure works. It's a snapshot system. Which means that if I start a transaction, all the reads that I do inside that transaction appear to have happened at the same point in time, even though things may have happened since then. It's as if I got a snapshot of the reference world at the point in time my transaction occurred. And I will only see values of references from that point in time or things that I myself have changed in my transaction. No other values. In addition, if I make changes in a transaction, when I commit, those changes will appear to happen, for everybody else's perspective, as if they happened instantly at the same point in time. So nothing is spread out over time. You're reading a point in time, you're writing a new point in time. And the effect of that from a consumer standpoint is you always see a consistent view of the entire world. Every reference you see inside a transaction, whether you're a reader or a writer. But the magic of multi-version concurrency control is that readers never block writers or other readers. They never block them. So there's a great amount of throughput as writers can continue to proceed. And writers never block readers. Because when you're reading the snapshot point in time. If you're reading time 10 and they've produced 11, 12, and 13, you don't care. As long as the system can continue to deliver you 10, you'll see the world as of 10. Okay? It's a very powerful system, and it's extremely easy to use. It does the right thing. There's one other thing. Oh yeah, and the other thing that the Clojure STM does is it supports commute, which is an interesting thing. Typically, sometimes some of the changes you need to make are commutative. Like you just need to increment a counter or add a value to a sum as a result of your transaction. Well, there's a way to do that, old school, right? Read, add, write back. As soon as you've done that, you've done a writing transaction to something, which means that nobody else could have written it. But if I'm getting something from a feed and you're getting something from a feed, and both of our jobs are just to like add them to this bucket, well, that's commutative. I have something, I can add it. You have something, you could add it. If I had to read, modify, set it, and you had to read, modify, set it, we couldn't cooperate. But since our operations are commutative, I could say, look, when this transaction completes, just add 1 to this. And you say, when this transaction completes, just add 1 to that. The order of those two things doesn't matter. And so the Clojure STM supports commute as a proper operation. All right, agents. Wow, time's flying. Agents manage independent state. The idea here is that there's a piece of state, an agent is responsible for it. You can get that state to change by sending the agent an action. An action is an ordinary function. It says take whatever your state is, apply this function to it, and that's your new state. The trick is you send actions to agents using a function called send or send off. That send, it returns right away. And what ends up happening is that request for the change gets queued up in that agent. And eventually, asynchronously, in a thread pool, that action will happen. This is for a much looser kind of concurrency, updating caches, updating incrementers, independent workers. It has a very high degree of independence. The nice thing about it is somebody else requests change, and they immediately continue their work. The change happens eventually in a separate thread pool. The agent system under the hood makes sure that no more than one action is happening per agent at a time. So all the activities on an agent are serialized by the system. That would be the hard part if you were going to try to do it yourself. So this beautiful non-blocking way, say do this work, and you know it will happen. If you say from a single source, do this, do that, do the other, this, that, and the other will happen in order. The cool thing about agents in Clojure versus, for instance, actor systems like Erlang is that the state is always available. If I want to go and see what the state of this guy is, I can just access it. It may not reflect all the actions that have been sent to it yet. But if you're using agents, it's because that doesn't matter to you. But it's extremely convenient versus systems where you have to make a request for a change and then make a request that somebody sends you a message back that something happened, which is how you have to do it in Erlang. There are lots of other cool features in agents. In particular, sometimes you'd like to make sure that the work you asked for gets done. There's a way to do that using await. So if you put in a wait message in a queue, you will block. And when the agent gets to that point in the queue, you will unblock. So I can say, do this, that, and the other thing, await. Now I will wait for you to do those things and come back. So there is some coordination available. If you have an agent's action sends other actions to agents, which is kind of a neat thing to be able to do, those things, dispatches get sent after the agent state has changed. So you can know, I've successfully done this, and now I'm ready to have you do the next step. Go do the next step. That happens in order. If you were to try to write in your program, you would see that you can't actually write it in that order. But the agent system will make it happen in that order. which is useful. Agents cooperate with transactions. They are a way to achieve once-only side effects in transactions, because what happens is if you dispatch an action inside a transaction, that will only get sent if and when the transaction commits. So even though the transaction may get retried and you think you're sending this message over and over, you really aren't. It will only ever get sent once. So if you want to tie some side effect to that, you could. Yes?
You can't use like a wait in a transaction?
Oh. Right, yeah, no, you can't do that. I mean, generally blocking in transactions is a problem because you're in a transaction and you're trying to get your work done and get out. Yeah, any blocking operation. It's important to note also that all these features, like for instance transactions, you don't need Clojure threads to do that. You can do the Clojure transactions on any thread. You can dispatch operations with executors framework in Java and run Clojure transactions on those threads. You can run Clojure transactions on the UI thread of Swing. I don't need to own the thread for this to work. But I would prefer that you not call agents actors, because actors are different. They're designed to serve the same purpose, but they're very different from, for instance, what's in Erlang or Scala. All right. Woohoo! So what are we going to do here? We're going to write a program. Well, I'm not going to write it in front of you. I wrote a program. That's a simulation of an ant colony. I should tell you right away, I don't know anything about ants, so this is not a very good simulation of an ant colony. But I guess you could use it if you did know something about ants to experiment with what would be a good simulation of an ant colony. And the idea is pretty simple. We're going to have a world populated with food and ants. And the ants are going to wander around, try to find food, bring it back home. There's a designated place in the world which is home. Along the way, they're going to drop pheromones. When they're doing their behavior, they're going to sense pheromones, they're going to sense food and sense home and try to make good decisions, mostly random, about how to leverage that information. In particular, we want the ants to act independently on real threads. Right? There's a lot of systems say, oh, we have threads, and they're fake, in-system threads. And fake in-system threads are over, because people are going to have these multi-CPU boxes, and you need to get on these other CPUs. So we need real threads. I'm not saying that this would be necessary. If you had this task to do, most people would just write a big loop, right? Tell each ant, behave, 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 then draw. Then go back and say, go, 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 then draw. I mean, I've done it a dozen times. But as an example of a system that would require a lot of coordination, doing it with multiple threads is a good example of what's hard about concurrent programming. So we're going to have the ants act independently. That becomes terrifyingly complex. We're going to throw in, we want to model pheromone evaporation, just because it's hard. And it probably is realistic. Also, the screen gets really ugly when it just builds up because it's green, and it just turns all green. So I need it to evaporate. But the idea is that by evaporating, only the valuable paths would be retained. We should have an animated GUI. Why not? What the heck? This is a couple of hour project in Clojure. And it ends up being really tiny. And as you'll see, pretty simple. So why should I update iTunes? I don't think so. All right. So what we have here is some Clojure source code for this ants program. This is running in Aquamax Emacs. You'll note my complete ineptitude at Emacs because I never learned it before I had Clojure. When I program in Common Lisp, I use LispWorks, and it has its own IDE, and I was happy there. But I'm really lucky that somebody's written a nice Clojure mode for Emacs. So I have syntax highlighting and a bunch of other neat features, only a fraction of which I know how to use. So I'll be fumbling along a little bit, but the idea is that up top here we have an editor, and in the bottom we have a REPL for Clojure.
You know how to increase the font size, though?
Oh, man. I'm already running at a pretty low res here. I'm not sure. I think you might want to move up if it's a problem, because I want to try to get enough on the screen at one time. It's already tough because I'm leaving room for my simulation over here. There's another seat here if you want. Are you okay? So the REPL, you know, so here's a little Clojure. It's a Lisp. That means that operations are in parentheses, right? And the operator is first. Right? And it seems like there's enough Lisp experience in the room that I don't have to explain that it's not function and then open paren. But it's the same number of parens. But Clojure's, you know, got, as I said, literals. That's a vector. That is a map. Okay, key value, key value, key value. You see it prints with commas. Commas are white space. I could have typed them in if I wanted to, but they don't do anything. Just a couple of other little quick things. Maps are functions of their keys, which means I have a map now in the operator position, and I can look up A. Let's see that. And we can just do a couple of quick thingies here just to show the immutability. Right, so we'll define M1 as this map of A, B, and C. You'll note it's a hash map, so the printing order is not predictable because it's hashed. And the function assoc, which is short for associate, will create a version of a map with the changes that you request. So I can, oops. Oh, oh, that's got to be this recorder thing. I bet you I timed out. Oh, man. Sorry about that. I don't think I've recorded something longer than this before. All right. Any questions? Yeah, if you want to get cozy here. What was I showing? Oh, I was showing you, so let's just make this map again. Okay. That doesn't cross my machine, so that's good. And then if I were to, well, let me save this one too. So key A 42. So assoc is what changes a map. Say associate this map at this key with this new value, gives you a new map. So there's M2. M1 is fine. Okay, this scales to maps with hundreds of thousands of keys. And what's neat about Clojure is you use maps essentially as little structures where you would use objects typically, and also as things where you would use hash tables to store lots of stuff. Same stuff. No reason to have two different things. They're both good for both purposes. So that's maps, vectors we saw, square brackets. I'll give you some heads up as to what we're seeing as we go through. It would be great if you could sort of get a sense, although I guess everybody here has used Lisp, so you know what it's like to work in a REPL. But to work in a REPL when you're working with Java, it was totally cool to do this program because essentially I built up my data and built up my representation and defined some stuff, and then I needed to see it, and then I started the GUI, and I could keep my GUI up while I changed it and resized it, and things that are just impossible in Java. Every one would have been a change the program, recompile it, reload it. So it's fun to bring that interactive development experience into the Java world. So let's look at what we have here. We're going to have a square world. It's going to be 80 units wide. We're going to keep track of the number of ants as the square root of the number of ants, which just makes some things later easier. So there's going to be 49 ants. We have values for number of places of food, the range of amount of food that goes in a place, some scaling values for the drawing, the rendering of pheromones and food, and evaporation rate. That's a pretty low rate. And some other factors here, times for how long we're going to sleep in the animation loop and in this ant behavior and evaporation agents. So def basically defines a global thing of that name with the value that's supplied. Again, if you know Common Lisp, it's a lot like def-r. Here we have def-struct, cell. And all def-struct does is define something that's called a struct map. And let me see, we should just do this as we go. So if I do this keystroke, I'm sending these guys to the bottom to be evaluated without having to copy them and type them. We'll make running true. So now I have a definition of a cell. Once you have a struct, you can create one by saying struct cell and then pass the arguments that were supplied to the def struct itself. So this will yield, what does that look like? Map. Structs are maps. Structs are maps with a little optimization, which is that I'm going to have a lot of these cells. In fact, I'm going to have 80 by 80, 6,400 of these cells, all of whom will have a food key and a fare key. So duplicating those keys over and over is a waste. By making a struct out of it, those instances of this map will share those keys. That's really all it does. But in every way, structs are maps. In particular, you can add stuff to them, just like you could any other map. There's that. Okay. So I've defined the struct for the cells. So each cell could have, it will have a count of food and a count of pheromones. I have in comments here, they may also have an ant in the cell. They may also be designated as a home cell. This variability in data is really cool versus objects where you say, every cell has this and these will always be false or some ridiculous value you don't need because it doesn't really have an ant. Either has one or it doesn't. Okay. So the world is a 2D vector of refs to cells. There aren't actually 2D vectors in Clojure. There are only vectors of vectors, just like there are vectors of arrays in Java. So this is just a little function inside. We can look at it. We're going to map. A fun is a literal. It's like lambda. It's a literal function whose argument we don't care about. We're going to create a struct cell object with no food and no pheromones, 0, 0. And we're going to call ref on that, which means we're going to create a reference around that data structure. And that reference is those refs I talked about earlier. That's something now that can only be changed inside a transaction. So we're going to end up with 6,400 references to these cell maps.
Just a dumb clarifying question. Map, the verb, is mapping functions onto...
They're both in Clojure. That's correct. This is map the verb.
Yeah.
Right. There are maps and there's map the verb. And welcome to not enough good words in English. Right, so let's make this. Boom. And now we have a world. So the world is there. Of course, because this is a vector of vectors, it's kind of cumbersome to always dereference that way. So I'm going to make a helper function called place. And that will let me find a spot in the world, a particular cell in this two-dimensional thing by passing, whoa, that's a weird-looking argument list. Because it's not just symbols, right? What is it? This is an argument list, and then inside that is a vector, right? This is an example of destructuring that I showed you before. This is a function that expects to get past a vector. And by writing the binding as a vector, it can name the pieces inside the vector directly, as opposed to saying, I take a vector called v, and then inside saying, and the first thing in v I want to call x, and the second thing in v I want to call y. By using destructuring, I can just directly say, I take a vector, and I'm going to name the first thing x and the second thing y. And that will be a place. So we define that function, and we can try it. What's the place at 22, 22? That's in our world, right? And we get back some ref. I don't usually care about the refs. I might want to see what's inside them. And we can do that by calling dref, or there's a reader macro at, which wraps whatever you pass as dref. So I can look inside that place, and I see, whoa, one of those cells. That's good. Everything's good so far. Now we have the same thing, ants. An ant has a direction always. Okay, the direction is, 0 is north, and then it's clockwise through 8. So it's a square world with square cells. And so an ant has a direction, but we also have the comment. It may also have food. If it's found some food, it will have a food attribute in its map, and that will be set. But that's optional. Now we can create an ant. Now, so here is the first instance where creating an ant is a destructive operation, because what's going to happen is ants are going to live in the world. And that's really where their data is going to be. So creating an ant means placing an ant in one of these cells. So when you create an ant, you're going to get two things. One is where does it go in the world? And the other is which direction is it facing initially. And now we see the first use of sync. Right, when I talked about you can only change references in transactions. Well, sync is the primitive that starts a transaction. So anything that's inside the parens of this sync is going to be inside this transaction. The nil is an argument that it's a placeholder argument, and eventually I think I got rid of these by making a macro down here. I got tired of writing sync nil, so I wrote a do sync. And eventually that will be part of Clojure. So to create an ant, we start a transaction. Then we say we find the place at that location. I just called place before, right? That gives us a reference to the place that we're going to call P. And we're going to create an ant by calling struct ant, like we said struct whatever before. With the direction, that'll give us a new ant object. And then we're going to call alter. Alter is one of the ways you can change a reference. There's set, alter, and commute. Alter is kind of the nicest way to do it, because alter says alter this reference by calling this function with these arguments. That's what alter means. So this says alter the thing at P, which we know is a little map, right? Associating ant with this ant we just created. That's going to change that. Now, that doesn't change the data structure that was there, right? We saw, what does assoc do? Creates a new map. It doesn't change the map that's there. So this is going to say, at that reference in the world, place a new map where there's an ant in it. Don't change the map that was there. That's going to get swapped out. So no maps ever change. No data structures in Clojure ever change. We're just saying this reference is going to point to a new map, which is the map that was there with the association with this ant. Okay, so just like we saw assoc before. So this is going to create a new map, taking what was in P, associating ant with A, then replacing P with that. That's what alter does. Calls a function of the state of the thing, yields a new state, puts that back in the reference. And then we're going to return an agent, which is the other kind of reference in Clojure, right? We had refs and agents. An agent that tracks the location. So the idea here is the world is a set of references to cells, and the cells have food, pheromones, maybe ants. Maybe they're marked as home. That is going to be a transactional world. We can only change it in a transaction. Then we're going to have agents, an agent per ant. And the agents are these asynchronous guys that are going to do work. Their state is going to be the location where their ant is. So there's a presumption here that no two ants in the same place. Not allowed. No two ants can occupy the same space. Now that would be potentially a hard thing to maintain. If you were to write this manually with locks and everything like that, you have to make sure no two ants can ever be in the same place. That's going to happen in this system. And these agents are going to be in charge of making sure that that's the case. So we're going to take the location we were passed and we're going to wrap it in an agent, and that's what we're going to return when we create an ant. We should try creating an ant. So we're going to define A to be create an ant at 0, 0 in direction 0. Oh wait, I didn't evaluate create ant. Now we've defined create ant. Now we can call create ant. So I'm evaluating this line here, create ant. A, and then we can see A is, it's just an agent. Agents can be derefed like references can, and we see it's 0, 0. But now if we want to look at that place, 0, 0, what should we see? An ant. Cool. And really, it was this much fun when I first did it. I promise. I'm going to move a little bit more quickly here. So there's an offset for where home is and a range. That's where I have the ants square root now, because what I need is a little square in part of the world where the ants start, and they all have to be in unique spaces. So therefore, look how convenient this is to have counted the ants by their square root. So we get a nice square big enough to hold the ants. Okay, so we have a setup function which is going to place the initial food and ants, and it's going to return a sequence of ant agents. Okay, so if we're placing food and ants, we're definitely modifying the world. We better be in a transaction. So there's our sink. Then we're going to go through for the number of food places. That was one of those variables earlier, right? We're going to go through, for each food place, we're going to find the place, pick a random place for the food to go, a random location, and we'll alter that location, putting in a random amount of food in the range of food we said before. So alter P, same thing we saw before. We're finding a place, but this transaction does, well, first of all, it's manipulating a lot of places, right? The number of foods, and it's also going through the home range, right? This is the list comprehension of Clojure called for. It says for each x in this sequence, whatever it is, and each y in that sequence, they're truly nested. So y's sequence could refer to x. Y's sequence expression could refer to x. For each of those, we're going to do some work. The real job of for returns a lazy sequence, but I don't have time to talk about sequences. Do all means make sure we touch everything in that sequence, because there's actually a side effect associated with this, which is to modify this place. That's all do all means. So we're going to alter the place. We're going to say this is a home spot. And we're going to put an ant there. Okay, so all the ants start at home. So it's going to create a little square and put all the ants in the square. Okay? In a transaction. So a whole bunch of things changed in that transaction. Bound, this is just a helper function for me. It's often in this world, well, first of all, the world is a torus. So I'm going to connect the sides around to each other, and I'm going to connect the top to the bottom. Everybody that's written cheesy games knows how to do this. And then you end up with a donut. So we have a donut world, right? The top wraps around to the bottom. The sides wrap around to each other. So between the donut world having to go from one end to the other and the direction world having to wrap around, this bound function makes it easy to say, take a number and make sure it fits in between these two numbers by wrapping. The WRAND, did I do bound? Okay, WRAND is a weighted random thing. So this is a way, oftentimes when you're doing systems and simulations where you need a random number, you need to make a random selection. And the things that you're picking from have different probabilities. You pretend you have a roulette wheel, right, where each slice on the wheel is a different size. Okay, and then you spin the wheel, and of course bigger slices have bigger chances of getting picked, and smaller slices have smaller slices. WRAND does that. Given a vector of slice sizes, it returns the index of a slice given a random spin with a probability proportion to the size of the compartments. That's a mouthful. We should try this one because I have no idea. But it takes, what do we say? It takes a vector. So if we said 1, 2, 3, 4, and this is going to return the index, I can keep trying this, and I should get higher numbers more often because they have bigger probabilities. Now if I change this to a really high number, I'm almost always going to get 3, right? So that's working. Direction delta, this is another helper function. It just says if I needed to walk in this direction, what would the x and y offsets be? What's cool about this function is what? How do we define all the other functions? Defun, defun. What's wrong with this function? It's not a function. What do we say about maps? Maps are functions of their keys. Direction delta, it doesn't need to be anything more than a map. You're going to pass it a number, you're going to get back one of these things. And it's going to work just like a function. Let's try it. Yay. That looks a lot like a function call. But that's a really cool thing to be able to do. You can write programs much more simply that way. Delta location basically takes a location and applies the delta and gives you the new x and y positions of the location. You can just trust me that that one works. Then I got tired of writing sync nil, so I wrote a little macro that does sync nil, and I call it do sync. From now on, I'll only use do sync. Okay, ant agent functions. We have a bunch of small behaviors. How are we doing for time? Do I need to like wrap this? And is everybody okay? We're gonna get kicked out of the room. Is this pace okay?
Yes.
You want to see what happens at the end? Yeah. Okay. So turn's an ant at the location. At this point, all these ant functions are going to affect the world, so they're all going to be transactional. So turn is going to take a location and an amount, right? It's going to start a transaction. It's going to find the place where the ant is. And in particular, these functions, turn, move, whatever, these are functions of the ant agent. What do we say the state of an ant agent is? Remember? It's just a location, right. So you'll see these are all functions of at least a location. They may have some other data, but all these functions about the ants are functions of locations, because these are functions, they're going to become actions of the ant agents. So remember, an action of an agent is a function of its state, possibly in some other values, but it's at least a function of its state. So all these things we're going to see about ant actions are actually ant agent functions. So this takes a location and amount to turn, right? We're going to find the place, get the ant that's there, which is just a piece of data now. Then we're going to alter the place, associating the ant with the result of altering the ant by changing its direction, that amount. Okay, so we create a new ant. We don't change anything really. Create a new ant, create a new cell with that new ant, and put that new cell in that old place. Because the only thing we can really change is the place, the reference. So this is programming with immutable data. We'll see that this is all really worthwhile, hopefully, later. But it's not actually that hard, even if it wasn't worthwhile, I don't think, when you get the hang of it. Does everybody see how turn works? And note also it returns location. This thing does not change the location, but remember, an action is a function of the state of the thing. So it better take a location and return a location, because it's going to be, the return value of this will be the new state of the agent. Okay? Now move. We move an ant in the direction it's heading. There's a caveat here that says you must call this in a transaction that's already figured out there's no ant in the way. Okay? And you'll see this function itself doesn't have sync in it. And if you were to call it, it would fail if you were to call it on its own, because you wouldn't be in a transaction. So this is saying you've got to be in a transaction. It ends up being inefficient to constantly recheck for the presence of the ant inside move. So the decision-making process of the behavior is going to find that we have free path here, and then call move. Absolutely, we can move, because I already checked there's no ant in the way, thus enforcing the no two ants in the same space. So how does this work? We get the what we call the old P, where we were. We're going to move from this place. That's where we are now. We're going to get the ant that's there. Right? We're going to get a new location by calling that delta function that figures out the new location. Oh, I didn't evaluate this. I got to make sure I evaluate. Make sure you catch me if I don't evaluate something. I don't think I did this one either. And we get a new location. We call that delta location function, which says, the new location is 2223 from where you are, pointing in the direction of the ant. And we find the place there, and that's going to be our target spot. We're going to alter the new place and put the ant there. Okay. We're going to alter the old place, and disoc says remove this key from the map. So there's no more ant in the other one. And then if it's not home, we don't want to spread pheromones all around home, because it just causes everybody to just stay home. So we don't drop pheromones at home, but otherwise when we move, we leave pheromones behind. Okay, so this just says if the place where we were isn't home, alter it, incrementing its pheromone. So a lot of work in there. A couple of places altered. This is a hard job with locks. Right, locks, what are you going to do? What order do you lock places in a world like this? Very hard. Very hard problem. Very easy. Well, here I didn't even show you how easy it was, because this function doesn't even do the transaction. Everybody good with that one? Remind me of this, because my program won't work if I don't evaluate all these. Take food. So here it says, again, you have to call this in a transaction that figured out there's food there. There's more than 0 food in this place when this is called. And same thing, find out where we are, get the ant there, alter the place, decrementing its food, and give the food to the ant. And put that ant back in there. Notice this alter, this assoc. took 2 key value pairs. Assoc takes as many as you need. So this is changing 2 attributes of the map and yielding a new map and putting that back in P. Returns the same location. Oh yeah, note move returned a new location. That's the new state of the agent, right? Is the new place. So that's one of the few that returns a different value here. So take food doesn't move you, like that. Drop food, same story. You have to figure it out in a transaction that you have food, and you're going to put it where you are. Same kind of thing. You're going to increment the food at the place where you are and disassociate food from you. Anne has no food now. All right, now we get to the behavior. This is a little bit more involved, but it's as complicated as this program gets. I need a helper function to rank things by some sorting function. So I don't want them sorted. I want their ranks. So what does it say? It returns a map of x's, a map of them to their one-based rank when you sort them by their key function. So I'm going to have a bunch of things. I'm going to sort them by some function, and then I'm going to return a map of the thing to its rank by that sort order. Just trust me that that works, because it's not that interesting. You know, it calls reduce and some other things, but it's really not that interesting. Behave. Okay, so this is the main loop for ant behavior. The ant agent is going to be executing behave over and over and over again. Each ant agent is going to be executing behave. So what happens? We're going to find all of our places. Where are we? What's the ant that's at the place we're at? Right? What's ahead of us? What's to the left? What's to the right? And we're going to make a list of places that are in front of us, kind of, which is ahead slightly to the left, ahead slightly to the right. We're going to use them later, so I didn't want to keep evaluating that. So we're going to let all these values. So that's all let does, you know, name, value, name, value. We're going to start a transaction. We're going to ignore these next 2 lines, next 3 lines for the moment. And we're going to look at the logic. Right? Basically, an ant is doing one of 2 things. It's either got food and it's trying to get home, or it's foraging. So we're going to say if the ant has food. And Clojure has common Lisp style truth logic, which is, you know, nil or false, because false has got to be there for Java, means false, and anything else means true. So I don't care about the value of food in the ant. I just care that it's there, and that will tell me that. So if I have food, I'm going home. So what are the cases, the conditions here? One is I am home, right? If this place is marked as home, I'm there. So the ant is going to drop the food. Oh, I got to explain this. It's going to drop the food and turn around. The arrow is a really neat macro. It basically is like a threading thing. It's going to say take location and pour it into the first function. Now this isn't even wrapped in a function, so it's going to make a function out of it called drop food. It's going to say drop food on the location and then take the result of that and thread it into turn. And that will be the value of the first argument to turn. Essentially, the effect of this is to say drop food of location and then turn of that for. But this is a more straightforward way to write it. It's kind of a chaining thing, that's right. So it's a function of location. Drop food at the location, then turn that thing by 4, which is the location. So that's what happens. We find home, we drop the food, we turn around 180 degrees. If we see that there's home in front of us and there's no ant there, we call move. Remember, it was a requirement of move that we be in a transaction, which we are, and we know that there's no ant in front of us. So those are true, and we can call move. These functions cooperate, you know, sort of very symbiotically. Otherwise, it's not one of those 2 things. So now we have to do some sort of selection. And this is probably too complicated to explain well, but I'll explain it quickly, which is that I need to rank the possibilities, 3 possibilities: moving forward, turning slightly left, or turning slightly right. Those are the 3 things I can do now, or that I'm letting the ants do. So I'm going to rank the choices 2 ways. One is I'm going to rank it by if there's home in front of us, that's worth 1. And this is a bunch of little neat Clojure stuff. One is sharp open paren is a function literal. So instead of having to say fun something and then write this and then that something here, I can say sharp the body and just use %, %1, %2, %3 as the positional arguments of this anonymous function. It's just the most succinct way to write an anonymous function in Clojure. But this is the same as fun of x if home x 1, otherwise 0. Just 2 fewer parens. It ends up being 7 characters shorter to do it this way. So when it's a short function, this is neat. Bigger functions don't bother with this. Write fun. It's not that hard. So we're composing that little function with deref because we need to get something out of the places. But essentially, we're sorting the places by their home content. And then we're also making another map, which is the places sorted by their pheromone content. Then we're merging these two maps with plus, which means we're going to combine at each key with the plus. So we're going to add together the scores from these two weightings. And we're going to use that to be the ranks. So we've ranked now the 3 choices. Then we're going to call a vector. And like maps are functions of their keys, vectors are functions of their indices. So we have a vector of the 3 actions. We might want to move. We might want to turn left. We might want to turn right. So we put 3 functions in a vector. Then we make a random roulette choice, right, of those ranks, picking one of those actions. That becomes the first argument of a function call on the location. This is probably just too clever. And I should have done it in more steps. But that's what's happening. So I'm taking an array, a vector of functions, choosing them with that roulette wheel thing based upon the ranks I calculated before. That yields a function, that expression, and that function I'm calling on the location. So am I going to move, turn left, or turn right? That's the whole case for going home. If I'm foraging, it's very similar. If I've found food where I am and I'm not at home, because you don't want to take food back out of your home, right? So if I found food and I'm not home, then I'm going to take the food and turn around. Hopefully turning around points me sort of towards home. Otherwise, if there's food ahead of me and that's also not home and there's no ant there, remember that was a caveat, then I can move. I'll go there, and then of course in the next cycle I'll take that food. Otherwise, exactly the same kind of logic, except, and the only reason why I duplicated it is because I thought I might tweak it, but I ended up not. Same kind of logic, except I'm going to rank the choices in front of me by their food content and their pheromone content. So I'm looking for food instead of looking for home. And the pheromones also, I try to stay on the paths, because theoretically the paths should lead to good things. That's why all the ants are on them. So that's behave. That's the biggest function in there, and that's the main loop of the agents, the ant agents. And finally, we have an evaporate function. What happens is the pheromones accumulate everywhere, but fresh pheromones are more valuable than really old ones. So letting them accumulate indefinitely is not that useful. And theoretically, in my very limited ant knowledge, I think pheromones evaporate. So we're going to make pheromones evaporate. Now, evaporating, that's a big job. To make the pheromones evaporate, I have to go through every cell because it gets all over the place, the pheromones, and I have to make there be less of it. So this is a function that's going to walk through the entire 6,400 cell world, and in a little transaction, 1 per cell, I'm going to multiply the amount of pheromone that's in a place by this evaporation rate, which is 0.99, diminishing it slightly, and putting that back in there. So I'm just tweaking the pheromones. So this evaporate function is going to be running, as we'll get to the simultaneity in a second. We're going to be running and walking through and making all the pheromones evaporate while everything else is going on.
Does something
Okay.
have to deal with the bottom threshold where it just zeroes out?
Well, eventually you're multiplying by 0, so. But I don't force it to 0. So you just keep getting smaller and smaller, and eventually you run out of float, I guess. Okay, so that's evaporate. Another use of the for, again, do run, because for is lazy, so I need to force this to happen. That's what do run does. And there's a mini transaction. Note this isn't a transaction around the whole loop. That would really, pin down the world, because this is a writing transaction, right? So, but I don't really care. I'm just supposed to evaporate everything, so I can do that in little jobs. There's a lot of little jobs to evaporate across the whole world. That's all the logic of the program. That's the entire simulation logic up there. So, let's have fun. UI. I need to use some Java stuff to do some UI. I need color, graphics, and dimension from there, buffered image from there, and this. And you'll notice already that this is smaller than Java. Yes? To do the same job, a bunch of lines in Java. I don't want 80 by 80. That would be too tiny for us to see, so I need to scale the world. So in pixels, it's going to be each cell is 5 pixels. That's what scale is. And then I'm going to do this backwards from render, because Clojure requires you to define things before they're used. So you're seeing definitions that are used later, but let's look at the overall picture in render, which is that we're going to be given a graphics context. I don't know, did anybody do Swing? Anybody ever done Swing? The idea is, there's a painting thread, and it calls you, and it says, here's a graphics context to paint into, and then you have to use it. So the cool thing about render is, what is the job of render going to have to do? Render is going to paint the whole world. Right? So painting the whole world means finding out where all the food is, where all the ants are, where all the pheromones are, and drawing that. It basically has to touch the whole world. But it only has to read the whole world. But I'd really like for this to be a high-quality report. And this is a classic problem. This looks like an ant simulation, but it's a really hard problem. Has anybody ever written an app with a whole bunch of stuff going on, and then somebody says, I'd like a report, and I want to make sure that nobody appears in 2 places at once, nobody's missing, all the values add up. And now you're saying, oh, I'd have to lock everything in order to have a valid report where everything's synchronized. Guess what? STM does this kind of stuff, and that's a very, very hard thing to do. So what do? We make a little transaction, and we rip through every place and put it in a vector. Boom, like that. Now, what do we say about transactions? When you read in a transaction, everything you read is as if a point in time. So even though you'll see the ants are going to be moving around and the evaporator is going to be evaporating things, this renderer is going to get a consistent view of the world when it does this do sync and runs through the places. Always. You will never see 2 ants in one cell. You'll never see a little crisscross of ants. If you counted the ants, they would all be there. And you'll have to trust me on that. But that's the deal. So we're not going to hold the transaction open while we're painting, because that's time consuming. So we're going to create a transaction, and we're going to run through every place, right? That's the whole range, and apply vector to that. So we'll copy them into a vector. Now we don't need to make copies of the maps, right? Because they're never going to change. So only the references end up in this vector.
So then you could also have the ants moving multiple cells between paint operations.
Oh, no, this is all going to happen at the same time. Yeah, everything is happening at the same time. While this is happening,
Right,
everything is changing.
But then, if the paint takes a long time before the next one happens, the ants may have moved multiple cells.
That's right. I mean, as in most animations of simulations, it's not a one-to-one relationship between. I mean, it would be easy to do that the old way. In the loop way, right? I would tick every ant, then paint, then tick every ant, then paint, and I would know that every paint cycle would show everything that happened in one cycle of the world. But I really want a more simultaneous world.
Yeah,
All kinds of things.
cycle slowing down.
Well, the other thing is some of these ants, I mean, this behavior is pretty consistent, but some of these behavior branches take longer than others. So in a real simulation, some ants may take more time to do their action than other ants. So there really isn't a notion of frame, 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 frame in the activity world. So we really have that independence. There's the activity world, then there's an animation, which are snapshots. But that's a very real-world thing. If you have a real-world system that has to do reporting, you have this problem. And if that real-world system is multi-threaded, you have a very difficult problem. I have yet to see an elegant solution to lock the world and give me a valid report. And what ends up happening is most systems have this copious logging and then time points, and then they recreate things backwards. So we copy the world very quickly, and then a lot of this is just basic Swing stuff. We're going to create a buffered image, which is not where we're drawing. We're going to create the image there, right? Do to is a way to do multiple operations to a Java thing. It's as if I called dot bg set color blah, dot bg fill rect blah, but I can say do to bg, and I don't have to say dot bg over and over and over again, which is already better than Java. So I set the background color to white, and I fill the rectangle. I'm going to blank out the whole thing, right? Then for every cell, I'm going to render the place, and render the place is a helper function, we'll see. And then we're going to go and create a box around home in blue. Right, so fill rect draws a solid rect, so that's a white background. We're going to look at render place in a second. Then we draw a rectangle around home, and then we take that buffered image and we put it into the panel, which is the thing you actually see on the screen. So we draw off in the background, then we paint onto the foreground, and that makes it animation, as opposed to drawing while you're showing, and then you get all flickery and nastiness. All right, so that's render. So render called render place. Render place says go through, it's called once for each place, and this takes the graphics context, the place, and the X and Y location. It says if there's pheromone there, draw some green, right, scaled by the amount of pheromone and that scale factor I said before. If there's food there, draw some food. Same thing, there's a food scaling factor, it's going to draw that. And if there's an ant there, we're going to call render ant and draw the ant. Then we have render ant. This is more complicated. In fact, I don't even use half of this. But the bottom line is, an ant is a little line. It's either red if the ant has food, or it's black if the ant doesn't. It's pointing in the direction. Believe me, that's not very exciting looking. It's like a dash. But we draw a dash for the ant. And finally, we had a helper function we saw. We filled cells in green and red and whatever. And so fill cell is a helper function that just takes the graphics context and does this. This is an interesting thing right here we haven't seen before, which is sharp caret. This is a metadata literal.
Rich, can you scroll up one that is right on the bar? Yeah, that's great.
Is that okay? So this is a metadata literal. This is metadata actually being supplied to the compiler. This is associating the metadata flag tag to graphics for the symbol G. And when the compiler sees that, it says, this G is going to be representing a graphics. It's a type hint. And we haven't seen any types so far, right? And Clojure is dynamically typed. But Clojure also supports type hints. And given just the hint that this is a graphics, all of the code in here will not use reflection. It'll generate calls to Java that do not use reflection. And you'll see there are only two type hints in this whole program. And that's all it takes to have this run fast enough to work. Given that this is a graphics, it knows the signatures of these functions, and they're called directly, no reflection. So what did we say? We did scale, so fill cell, render an ant, render a place, render the whole world. I need a panel. That's a graphics thingy, right?
That's your window.
JPanel, paint. I've just defined an instance of a derived class of JPanel and defined the paint function. That's it. That's all it takes. So you say proxy, you put one or more, one class and one or more interface, 0 or more interfaces, and you'll get a proxy class defined that implements that, is a derivee of that class and implements those interfaces, and then you can supply closures in here that define the function. So we only care about paint. Paint gets passed, like I said, paint is a Java function now. This is going to be called from Java. It gets passed to graphics context, and it's going to call that render function. So this little between here and there is all it takes to define a derived Java class in Clojure and implement its function. And then this due to is that same thing. I'm going to create a new one of these, and I'm going to immediately set its preferred size. So due to this new proxy, set preferred size, this dimension. Okay, so I'll make one of those. Oops, I have to be here. I have 2 panels now. All right. Frame is make a new JFrame. So also use due to. Look how fast and easy this is, not multiple lines. Due to a new JFrame, add a panel, pack it, and show it. Cool. I wonder what happened if I called that. Wait, I just did. Oh! Whoa, cool. We have a world. Oh, we have the ant we put on it before. Right? So, I mean, I programmed in Java and C#. I never did anything incrementally like this there. I mean, this is so much fun.
Rich, can you move the frame down so
I don't know what. Oh, what's happening? I'm not seeing that. I'm not catching it. So is this going to be a good place for it? Okay. Cool. So we're drawing. I like that. And now we need to just do the agents part, right? Like nothing's really happening. This is a pretty boring world. We haven't populated it, right? We didn't call setup, and we didn't start any activities up. So we'll just look at. We saw the behave function, which is the main action of the ant agent. We're also going to have an animation agent, whose job it is to call render. To call repaint, essentially. So we'll make an agent for that, and he really doesn't have any useful state. So animator is an agent with like nil as its state. His job is really just to perform side effects. And this is going to be his main action. We're ignoring the running part now, but his main action is to call repaint and then sleep. That's what the animation actions does. And then there's another agent. Again, he doesn't have very useful state because he's mostly being run for side effects. The evaporator. And his main action is evaporation. And he's just going to call evaporate and then sleep. Okay? So we have an animator agent with an activity for him, an evaporator agent, an activity for him. We already defined the behavior for the ant agents, a bunch of those. So now we've seen this run. We just want to go check up here. Running is true. I don't know if I ever did this, but make sure we did. Chances are good I forgot to evaluate something, so I may want to load this file. But I'm not going to, and we'll see what happens. So we can look now at those lines I told you to ignore. I'm sorry I'm scrolling so much. Okay, this is now, we're inside behave. Oh, wait. There we go. We're inside behave. And we said do sync, and we said when we're running, send off, which is one of these send in action, send off to star agent star. Star agent star is this agent that's currently running. Right? Because on any particular thread, there can only be one agent at a time. We know that this behave function is an action, which means it's going to be called on an agent, which means that this value of agent will be bound in this action to the agent this action is being called on. So this is basically saying, send myself, this same function again. Do it again. So each agent is going to be told to do something, and when he does it, he's going to tell himself to do it again, one more time. Those will all get queued, because we know when you send a dispatch an action, inside an action, when does it go off? After your state changes. So that's when this is going to happen. Even though it comes at this point in the code, it's only going to happen after a state changes. So he's going to behave once, and he'll have sent himself a message, a reminder, behave again, as long as running is true. Similarly, if we now look at the parts of these other functions we weren't supposed to look at, the animation thing does the same thing. Send the agent that's currently executing animation again. And the evaporator does the same thing. So these guys are going to be in infinite loops, broken by running. Okay, so far? Yeah.
That star agent star a magic variable.
Star agent star is an example of a var, which I didn't talk about, but vars get bound thread locally, and the agent system will bind the var star agent star to the currently executing agent. That's part of the agent system. So because, remember, agent functions are functions of their state. They don't really have access to their reference, except this way. It's a nice way to do it because most functions of agents are really just functions of their state, and they don't need to access this. And then you can test them independently by making them functions of data as opposed to functions of references. Yes?
This may be a dumb one, but to me, the def evaporator and the def and evaporation, they look like separate expressions to me. What's tying them together?
Nothing. I haven't sent. I'm going to send the evaporator the evaporation action in a minute. They're not connected. Okay. So normally I wouldn't have done all this independent evaluation, and I just would have loaded this file. I'm going to see if I actually got everything. So we remember, I don't know if you remember, but up at the top when we called setup, right? Setup distributed food and setup home and put ants in home, and it returned a sequence of the ant agents. So if I call setup, I'd like to keep track of that in ants. I'm going to do that here. So I'm going to call setup and capture the list of agents into ants. Woohoo! So what's in ants? Wow, a lot of agents. Cool. So we have 49 ant agents now. Now we have the first use of agent actions. We're going to send the animator the action animation. Remember, actions are functions. The animator is an agent. We created him before. So we're going to send him animate. And he'll do that over and over. Whoa! Cool. He's animating now. I should have done thread counts before. Let's see. So I don't even know where we are yet. We'll have the most threads soon. Let's just put it that way. Okay, but there was a thread created, and that thread is running this animation loop. But nothing is changing yet because we haven't set the ants off. So now what I'm going to do is, again, this do run is because map is lazy. So if I said map this function across the ants, it would do the first one. But if I never consumed the result, none of the other side effects would happen. So do run just forces the side effects of what would otherwise be a lazy functional thing. So we're mapping send off to this ant behave. This is just a quickie function literal. So we're sending behave to each ant. We're mapping this function across the ants and then forcing it to happen with do run. So, whoa. Cool. There they go. And then we're going to start the evaporator. So now the evaporator's going. And if we look here, whoa, now we're tops, 68. 68 threads. We're using more than 100% of the CPU, which means we are using 2 CPUs. And we're cranking away there. And there we go. Ants turn red, remember, when they have food. So there's red ants, and the green is the pheromone buildup. We have an animation. And that's multi-threaded programming in Clojure. No locks. Some of what's happening in here would be extremely difficult to do with locks, or impossible. The graphics rendering has got a consistent view of the world, right? It's not necessarily the latest, but when you really think about worlds, there's no such thing as the latest without stopping it, right? It has a consistent view of the world. Evaporation is this big time-consuming job that's running in the background. Each ant is looking at a set of things, a set of places, and making decisions about what to do. Those sets of places can overlap, and those decisions can conflict. But by running them in transactions, the constraints of the system's logic are enforced. So no 2 ants in the same place, no taking food from home, and et cetera, et cetera. And the drawing is not impeded by the ant motion, is not impeded by the evaporation. There's 51 threads associated with this, right? 49 ants, an evaporator, and an animator. We'll let that go. Does anybody have any questions? Yes?
I remember reading that there was a thread pool for agents.
Oh yeah, no, this thread pool's behind this.
But it's not one.
Oh, okay, so yes, all right. So there's a thread pool. Oh, sorry, I blocked our view. There's a thread pool. There are actually 2 thread pools in the agent system. One is used by the function send. The function send uses a fixed thread pool. That's a multiple of the processors. Well, it's related to the number of processors. There's also send off, and send off will allocate a thread per request. And the idea is that if you had requests that might block, if you have actions that might block, you could consume your thread pool with send. Right? So anytime you might block, you should use send off. Because these ant threads are sleeping, that's technically blocking, and the right thing to do is use send off. And so what I've done here is use send off. I could re-architect this to use send and make the weights much smaller than they are, because now each ant will be waiting in a shared set of threads and get exactly the same behavior. But that's a choice you have to make. If you only had a fixed thread pool, you couldn't have blocking operations. If you only have a thread per operation, you can't get maximum efficiency, because a fixed thread pool is the most efficient way to crunch calculations. So the agent system gives you both. Also, remember, you could use for transactions only. You could also put Clojure functions into the executor framework of Java. I'm not against that. It's a good framework, and it has futures and some other features. So you have to pick the right tool for the job. But these are pretty high-power tools with very low overhead ease of use. Like, all we did was put sync around stuff, pretty much. Any other questions? Any other questions about Clojure generally? Yes?
Not a question, but since the recording got screwed up, you might want to plug your TV screencast.
Yes, Blip TV is good. Oh, I should just put up my... yeah, you can find out, really what I would just say is go to clojure.org. On there are links to the Google group, which is the main way we communicate. There's an IRC. There's also Blip TV, which is a place where I put screencasts. Like, maybe I'll put the first half of this talk if it ended up on my hard drive intact, which is probably not the case. But I am doing a series of things. It's likely I'll give this talk again, because I prepped all the slides. And I'll make the slides available. And basically everything Clojure you can get through the site. If you look in the upper right, you'll see nav to the wiki, Blip TV, which has a bunch of talks I've given on sequences and some of the other core data structures of Clojure. If you want to start from scratch with Clojure, some of those can be useful, if somewhat informal. They're like lunchtime talks I gave. But yes?
That's awesome. Thank you. You mentioned Erlang a couple of times, and I'm curious. One of the things that the Erlang community differentiates, or says is distinctive of Erlang, is the distributed concurrency.
Yes. Yes. Clojure does not yet have a distributed concurrency story. Erlang made a very conscious decision to unify their concurrency primitive with distribution. And there are a bunch of trade-offs associated with that. It makes it transparent to distribute things. At least it makes it code transparent to distribute things. That is, you don't have to change your code. You can move your process to another machine, and it will work. In practice, there are behavioral differences to moving to a different machine, which is that if you were sending a lot of data and it was local, it worked. And now that it's across a thin wire, it doesn't work so well. There are some good papers from Sun, I think, that are critical of transparent distribution. I happen to be sympathetic with those papers. But I think for the problem domain they were in, they valued the transparent distribution more than the others. The other thing about having transparent distribution is that all of your failure modes are failure modes of distributed systems, which are the worst failure modes. In other words, they have to build systems where every interaction is as if it could have the failures, right, could have the failures you have with a distributed system. The other major difference, I would say, between the actors of Erlang, because Erlang is really an actor system. So it's actually kind of a very pure rendition of the original actor model. The difference between actors and agents is there's no access to actor state except via a message send. And that's because that's the only thing you can distribute. Clojure agent state is directly accessible. It cannot be distributed. And so there's a trade-off there. I find that the ease of use of programming with direct accessibility to that state is worth distinguishing the two systems, a distributed messaging system and an asynchronous messaging system for in-process. So that's what I did in Clojure. I anticipate looking at a distributed system for Clojure, but it will not be a unification of agents, and it will be distinct.
So it would be like a fourth kind of.
Correct. It'll be like a fourth thing. I don't know if it'll even feel like references because, at a certain point it may be easier to wrap JMS or something like that. But those are the trade-offs. So that's why I said agents aren't actors, because they're different. And they're strictly not better or worse. They're trade-offs. They have different characteristics.
We talked about Erlang too. One of the nice features of it is kind of hot swapping out code, because you're passing all the state pretty much every recursion round. Can you do something like that?
Oh yeah, I can change this program right now.
So as it's running, an older agent can be running.
Oh yeah, I mean. Well, it's not the same. I mean, essentially, what they do is they down processes to start them anew with new functions. So they're like the system keeps running, but the system keeps running because the system is designed to tolerate processes dying and they're restarting. That's how they keep running in Erlang. Here, this will literally keep running. There are other big differences with actors and agents, and one of the things I like about agents is an actor is waiting in a message loop for things it anticipated having been sent. Right? You're in a loop. You've got a pattern match, right, against messages you were predefined to receive. I can right now send a new action to any of these agents that are running that it never knew about. In other words, I can define a function that's a function of the behavior of an ant. Like I could call drop food on all ants and they would drop their food where they are. They're not waiting to be told drop food. Like no one's waiting to be told, fall down or get hit over the head. So in simulations, I think, building something that knows it could do X, Y, and Z means limiting a system to doing X, Y, and Z, or downing the system, downing the process, and starting it with a new function. So they have code loading. It's tied into process regeneration. Whereas in Clojure, I could change the function that draws the ants right now to draw them in a different color. Let's just do it.
Yeah, I was gonna say, those are a bunch of lines. I can't even see ants.
Well, I'm not going to change. I'm not going to change them into
That would be
graphics or anything. So what's a color? What is this? Red. This is my red one. So we can make them. No, yeah, red, green, blue. So I can make them purple, right? Everybody see red? Some red. Oh, purple. Okay. No problem. No problem changing the functions of this thing at all. I can change any of these functions while they're running. They'll be instantly used, and they will not stop, and they will not drop their state. So it's different. I mean, I don't want to beat up on Erlang. I think Erlang is very cool. I looked a lot at Erlang, but in all of these things, there are multiple decision points, and design is about choosing between trade-offs, not right and wrong. So Erlang has a much better distribution story than Clojure because it has a distribution story. On the other hand, I would find it extremely tedious to have to wait for messages in order to read state of agents. And I think that's a recipe in Erlang, and they'll admit it, for manual deadlocks, because you have to set up, I sent you this and I'm waiting for you to reply back to me, and you go into this nested, I'm waiting for a response from Fred. And it's possible to write deadlocks that way. You can write deadlocks with a wait in Clojure, but a wait you're really using strictly for synchronization. In order to read somebody's state, you don't need that. So it's a little bit different. In every way, there are distinctions between the two. But yeah, hot code loading, sure. Change the behaviors as they're running. No problem.
When you do a hot code load like that, renderant is a var, right?
Yes.
And you are changing the binding of the var when the compiler recompiles the bytecode?
Correct. That's one of the reasons why vars are mutable at the root globally, so that you can redefine functions.
What if two people were trying to do that in the same thing?
Don't do that. That's def. I mean, what I did to do that is I called def. Def means establish this as the meaning of this thing. It's not set. In fact, you can call set on vars, but if you call set on the root value, you'll get an exception. That's not allowed. So in programs in nested context, when you want to call set, you better have a thread local binding or it will fail. So you have to distinguish between def and set.
Would you disallow that when you do that programmatically anyway if you try and do the wrong?
You can't do the wrong thing with set. But def is an absolute. I know what I'm doing. I'm in charge of the world, and I'm defining what this means for everybody. And the only reason why there's that hole is because you have to have it in order to have programs where you can fix them without restarting them. There has to be something that's settable like that. And so the root values of vars are that way. Other questions? Yeah.
Another question. In some of Simon Peyton-Jones' talks about Haskell, he draws this chart where you have, safe languages, and I forget what the axes are, but he's talking about features coming over into C# and Java, these other languages, sort of functional stuff coming over. Do you see some of this stuff, especially because of your interop, being, amenable to being incorporated into Java? I don't care because I don't use Java, but I'm curious.
I would hope not. I mean, I would really love for Java to not change at all anymore. Because right now, Java is my infrastructure language. If they make it more complex, they make my interop job more complex. But I do think that there are fundamental problems with languages like Java, in that when you say class blah, you start with a mutable thing. You have to expend effort to do the right thing. And even then, like the Java book talks about concurrency, but if you do that and you don't have like the persistent data structures of Clojure, you really can't effectively use large immutable collections, because to change them means to copy them. So it's a bigger story. You can use the Clojure class library from Java. I mean, it's a very nice class library, and I'm really proud of it. And it's somewhat awkward and non-idiomatic to use it from Java, but you can use all of this from Java. You can write Java programs that use all of the Clojure stuff.
I've done a couple of little toy languages. Just curious, from like idea to getting the REPL working, how long of a span was it? Working on it.
I've been working on Clojure for a couple of years, 2 years. I mean, I've been playing around with the idea of trying to make Lisp and Java interoperate for 4 or 5. But Clojure as a language, it's been through a large genesis. I mean, it supported C# for a while. It was a compiler written in Common Lisp that generated C# and Java source code. And it was only over the summer that I decided to stop supporting .NET and to try to focus on compilation to bytecode. And then, because that's where they differ. When I was generating source code, they're pretty similar. I mean, annoyingly different, but not appreciably different. But then I decided to generate bytecode, and it's greatly accelerated the completion of Clojure. And it's ended up much more dynamic, and the intimacy with Java is a big payoff. And now that Java is open source and the libraries are so available, I'm completely happy with where it's ended up. But it's a huge amount of work. The thing with Clojure is it's less the compiler. I mean, one of the things, I'm presuming some knowledge of Lisp, but almost all the things you're seeing in Clojure, for and that destructuring binding, those things are all written in Clojure. I added for, you could have added for. That's just a macro. Destructuring is also just a macro. I didn't change the compiler one bit. There's nothing there. The compiler is a super primitive Lisp. It has if, set, def, and lambda, fun, and 7 other things plus 5 for Java. There's about a dozen primitive things, and the rest of Clojure, the language, is written in Clojure. There's a boot.clj. It's like a tour of a language self-constructing. When is defined and conned, and nothing exists before that thing starts, pretty much. But a big part of Clojure is this class library was this huge job. The persistent data structures are a big deal, and they're a core underpinning in how Clojure works. It's a big class library, so that was a big job. Much bigger job than a Lisp compiler, I think. Anything else? It has a lot of attributes you're not necessarily seeing here. Like, it's very fast. You should find it faster than Python or Ruby or any of those by a significant amount. And with hints in every area other than arithmetic, because all numbers are boxed in Clojure. calling speed should be equivalent to Java. On my desktop machine, I can make 10 million function calls a second in Clojure. So it's suitable for real applications. The persistent data structures are in striking distance of all the Java data structures. That's within a factor of 2 to 3 or 4. But the benefits from using them are immense. Just try thinking about doing this program the way you would have, with cells that you would change in place and locks. Because, the immutability, it's kind of subtle. For instance, this render, it snapshotted the world. Well, it couldn't have if those maps inside the cells were really changing. But they're not, right? They're getting swapped out. So when it scans the world, it captures maps that will never change. That scales up globally to the way you think about writing programs. When you know your data can never change out from underneath you, everything is different.
And there's still garbage collection for all of those.
Absolutely. Correct. If you don't track your trail, it goes away. And one of the other key things, if you're thinking about targeting Java with the language, the ephemeral garbage collection in Java is stunningly good. It's really, really good. And it's a premise of Clojure that it be considered free. For instance, there's the sequence operation in Clojure, which is like cons, but it's an abstraction. When you use that abstraction on a vector, for instance, you have to allocate memory every step. That is so cheap. It's just a pointer bump. And because it all ends up in Gen 0, it's nothing to GC. And the things I see Hotspot doing with Clojure are really great. It loves all final classes. It just loves Clojure code. So it's really good. Anything else? Well, look, they work. Look, they've put all this food around home. I can't actually say that they wouldn't have done it if they were behaving randomly. I mean, just from encountering home. I don't really know that I have a decent behavior. I just know that they don't get stuck banging into each other like they did the first few times I tried. Well, thank you. I really appreciate you hanging out here.
How'd you come up with the name?
I did a Google search and I had 0 hits. I grabbed the domains. I was so happy.
You did the,
My brother did the logo. Yeah.
Much better than the Haskell logo. I think it's a big seller.
It's got to have a good logo. It has it all, right? Oh, good. You saw it all, right? Peace and yin and yang. That's right.